Welcome back, and this is the first in a series of videos looking at the alkenes. So you're going to need your notes, and we're going to start off by looking at sigma and pi bonds. So the general formula of the alkenes is CnH2n. You do need to be a little bit careful because this is also the general formula for a cyclic alkane, so don't get those two muddled up. Now, alkenes, again, are hydrocarbons. In other words, they contain carbon and hydrogen only. They're aliphatic because they are straight-chained with no aromatic groups in them. Unlike the alkanes, they don't have the maximum number of carbon-hydrogen bonds, so they're said to be unsaturated. Simple alkenes contain one carbon-carbon double bond. Now obviously we can't get an alkene with only one carbon because we need at least one double bond. So the first member of the alkene family is actually ethene. Now we need to understand that there are two different types of bonds in the carbon double bond. There is a sigma bond and there is a pi bond. So sigma looks like this and pi is this one. And when they react, it's the pi bond that breaks, not the sigma bond. The reason for this is the pi bond is weaker than the sigma bond, which is why a double bond is not double the strength of a single bond. It's stronger than a single bond, but it's not double the strength. So if we look at the sigma and the pi bonds on a normal carbon-carbon double bond, we have a sigma bond which lies between the two carbons. That is my sigma bond. I'm just going to label that as my sigma bond. And then our pi bond lies above and below the carbons. And this is one pi bond. So there's my sigma bond and my pi bond, which lies above and below the plane of the molecule. So the sigma bond has a single area of orbital overlap and it overlaps horizontally. So we take two p orbitals, we have an area of overlap there. That is my sigma bond. So it has this single area of overlap and it's overlapping horizontally or end on end or head on or direct. A pi bond, on the other hand, has two areas of orbital overlap and it has a sideways or parallel overlap. So, for example, if I draw again my p orbitals, there's one p orbital and it's overlapping and it's got an area of overlap here and here. So it has these two areas of orbital overlap. You can see them here in the shaded area, and it's a parallel overlap. So this develops into these two areas above and below the plane of the molecule, whereas this one just converts into a single area between the two nuclei. And this helps us to explain why the pi bond is weaker than the sigma bond, and hence why the pi bond breaks in the reaction but not the sigma bond. There's a good overlap of the orbitals in the sigma bonds, whereas because the p orbitals are overlapping in parallel, that's a much poorer overlap. Also, the overlap of the orbitals in a sigma bond is along a line between the two nuclei, whereas again in the pi bond there is sideways overlap. So that means overall that the pi bond is weaker than the sigma bond. So there's this good overlap of the orbitals in a sigma bond, and that sigma bond lies along an imaginary line between the two nuclei. Whereas because the pi bond forms from parallel overlap, that's a much poorer overlap, and they're not in line, they lie above and below the imaginary line between the two nuclei. So we have the same naming rules that we had for the alkanes. So the prefix eth tells us that we have two carbons, and the suffix -ene places it in the alkene family. So again, that general formula is going to be CnH2n. So ethene, that should be ethene, has the formula C2H4. So drawing them out as normal, this is what we get. So we get ethene, we get propene, which now has 3 carbons in my longest chain. This would be methyl propene, because this is my longest chain with the 3 carbons, and then I have a methyl group on this middle carbon. Technically, I don't need a number because there's only one place for that methyl group to go. But if you want to, you could also call this 2-methyl propene. Showing it as skeletal formulas, you simply show it as a double line representing the double bond. So again, there are my displayed and skeletal formulas for the first 2 and the first branched alkene. So we name them in the same way that we named the alkanes. We look for the longest chain of carbons, which in this case is 3, so that will be prop. It's got a double bond, so that's going to be propene. So it's going to start with a propene, but it's also got this methyl group here, so this will be methyl propene. This one, slightly more complex. I've got 1, 2, 3, 4, 5 carbons in my longest chain, so that's pent. It's got a double bond, so it's pentene, but there are different places that that double bond could go. We always remember number it so that the functional group has the smallest possible number. So that makes that carbon number 1 and that carbon number 2. So this is pent 2-ene. It's got 2 branches on it, a position 2 and position 4. They're the same functional group. They're both methyl groups. So this becomes 2,4-dimethyl. Can't quite fit in. Pent 2-ene. So just drawing that out a little bit better there. But you do need to remember to count the number of carbons in the longest chain and also to number the chain so you get the smallest possible number for the functional group. And you'll practice a lot of these in class. So we started looking at isomers in your alkanes notes, and we're going to go on and look at them again. So isomers can be split into 2 main groups, structural and stereoisomers. We'll come back to stereoisomers a little bit later, but we're going to look at structural isomers in this case. Now we're dealing with alkenes, but also remember this general formula is also the formula for a cyclic alkane, so they will show functional group isomerism. Position isomers, that's generally to do with the position of the double bond. And lastly, chain isomerism is to do with the carbon skeleton. So a good example of this is C4H8, which has chain, position and functional group isomerism. So there we have but1-ene and but2-ene. Notice that we've moved the position of the carbon-carbon double bond. Methyl propene is a branched molecule with that methyl group on the second carbon. And last but not least, cyclobutane is a functional group isomer because it doesn't contain any carbon-carbon double bonds. It's an alkane, but it's a cyclic alkane, so it has the same general formula as an alkene. So the but1 and the but2-ene are position isomers. But2-ene and methyl propene are chain isomers, and but1-ene and cyclobutane are functional group isomers because they contain a different functional group. So you need to be aware of all 3 types of isomerism. So alkenes can not only show these types of structural isomers, but they can also show stereoisomers. They can show what we call geometric isomers, and that's what we're going to look at next. So geometric, sometimes you'll see it called EZ isomerism, occurs because there is no free rotation around a carbon-carbon double bond. The carbon-carbon double bond restricts rotation. it will rotate at very, very high temperatures. So try to avoid saying things like there is no rotation. There is no free rotation, or there is restricted rotation around the carbon-carbon double bond because of the way the pi bond is arranged. So as long as you've got that carbon-carbon double bond, you have the potential to have geometric isomerism. But it's not enough just to have a carbon-carbon double bond. You have to have different groups on each of the double bonded carbon atoms. So on each of the carbons of the double bond, you have to have 2 different groups. Now, for some reason, students always remember the restricted rotation around the carbon-carbon double bond, but they always forget this second part. And this second part is very important. If you don't have different groups on each of the carbons of the double bond, you're not going to have geometric isomerism. So if we look back at our C4H8, our butene molecule, only the but2ene will show geometric isomerism. And there are 2 versions of this, trans and cis. Trans is where the methyl groups are on opposite sides of the molecule, and cis is where they are on the same side of the molecule. So if we draw a trans but2ene, we have our carbon-carbon double bond, and in this case the methyl groups are on opposite sides of the molecule, and I have the hydrogens here. Whereas cis-but2ene, the 2 CH3 groups, the methyl groups, are on the same side of the molecule. Now these molecules can't be interconverted because this end can't be twisted because of the restricted rotation of the double bond. But notice but1ene would not show geometric isomerism because that would have 2 hydrogens on the first carbon. So we have these 4 molecules here, and we're looking at whether they are cis or trans. So this group here, we've got these 2 CH3 groups on the same side of the molecule, so this would be a cis version. Here, cyclic groups, again this time it's the circle that's providing us with the restricted rotation. So we have chloro groups below and a chloro group above the plane, so that would be trans. Then we run into a little bit of a problem. We're not sure on this next molecule, am I looking at this chlorine and this CH3 group, in which case it would be a trans, or am I looking at this chlorine and this bromine group, in which case it would be a cis, so we're not sure. Likewise here, we're not sure if we're looking at the 2 CH3 groups or the CH3 group and the chlorine, so there's a problem with these 2 molecules. And this is where the cis-trans system starts to break down. We're not sure which of these groups has priority. So in this case, we need to use the new naming system, which is called EZ, and that's the one we generally nowadays use in chemistry to decide whether or not we have the different types of isomers. And all the molecules you'll be naming from here on, we're going to use the EZ naming system. So that finishes this first video, just introducing the alkenes, looking at isomers, and starting to look at geometric isomers. In the next video, we're going to go on and look at the EZ naming system. But you're going to practice a lot of these in class. So until then, stay safe. See you later. Bye bye.